All right, so we're talking about proving similarity today. And so far, we started with a Kahoot that reminded us about how to prove congruence. So we remember, and you don't have to write this into your notes, but this is just what we did. Remember, to prove congruence, we could use transformations with rigid motions. So we could use rigid motion transformations. Which ones were my rigid motion transformations? Which ones were those? Give me one, Juliana. Rotation. Give me another. Drew, not Drew, Donovan. Rotations, reflections. Came. Translations. Translations. And anything else? No, those were the rigid motion, right? These were also called isometries. So I don't know if you're familiar with that word, but isometries, they preserve size and shape. Okay. To prove similarity, and maybe we should start by reminding ourselves what it means to be similar. What does it mean to be similar? Donovan? Same shape. Okay, so really the one that we're focused on here, similar figures preserve, oh wow, that's not a P. Preserves angle measures. So if you want to know if you've got similar figures, check the angle measure. So similar figures preserve angle measures. And right now, what we're really focused on today is to prove this. So to prove similarity, we just have to show that there is a sequence of transformations that maps the preimage to the image. And really, we get one kind of neat, super neat thing from this. And let's just do it by quick example here for the first thing that we can see. Let's say that I start with, maybe I start with this. And I call it circle C. We've got circle C here. And I'm going to move circle C over 8 up 3, and then I'm going to change the size. So let's do this. Maybe I put it here instead. And then I change the size to this. So let me get rid of that extra dot, erroneous dot. Oh, that was too much white out, but y'all. Are these figures similar? Let's assume that they're actually good circles first. Are these figures similar? Yeah, how do we know? They're both circles, but Katie Nielsen, explain it a little bit further if you can. Okay. So let's use these words here. If it preserves angle measures and to prove similarity, I have to write a sequence of transformations. What sequence of transformations could I use? Give me, Juliana. I would use a translation and dilation. Now, wouldn't that be true for all circles? Couldn't I just move and then grow or shrink a circle? Does anything else about circles change when you translate them? If I rotate a circle, does that change the circle at all? No, not even a little bit. So what we get is actually this kind of interesting fact that all, and it means all circles, are similar. All of them, each and every one. All circles are similar, which maybe kind of just is a no duh and not worth anything, but it is nice to know that all circles are similar. Okay. Now we do have some things that we need to discuss when we're dealing with similarity itself, and let's start by looking at a little bit of an example here. So let's say it like this. Let's look at a little bit of a review here. We'll keep relating this to congruence. If I say that triangle ABC is congruent to triangle, let's call it JKL, AB is congruent to what? JK. Right? And we could keep going here, and we could say that AC is congruent to JL. And how would we know this? What was that acronym? Heard somebody say it. Right? CPCTC. Okay, congruent parts or corresponding parts. So AB corresponds with JK and AC corresponds with JL. Corresponding parts of congruent triangles are congruent. This is our CPCTC. Well, the thing is, we've got something kind of similar for similarity. Okay, and we have to name them as such. So if I give you two triangles here, let's call them like this. And maybe this one goes out here. And I call it A, B, C. And then I've got this triangle here. And I say that this is, oh, I don't know, D, E, F. I could say that triangle ABC is similar. Okay, this is the symbol for similar. It means is similar. Is similar to ABC is similar to which triangle? I would have to go in the same order. So D to E to F. Let's ask it like this. Triangle CAB is similar to which triangle? Gavin? FDE. Okay. So the things still need to correspond to each other. The angles still need to match up. The sides still need to correspond to each other. Let's see. Let's say that I've got a figure here, and maybe I just make up some, but maybe I don't. Maybe we'll just do this one. If I want to know if two figures are similar, so let's say that I've got this. I've got A is at 1, 1, and B is at 2, 4, and C is at 3, 9. And then somehow this shape gets changed, and it gets changed to this. D is 1.5, 1.5. E is at 3, 6, and F is put to 4.5 and 13.5. I want to know, are these figures similar? Well, in order to prove that they're similar, I have to know if there's a transformation or sequence of transformations that takes me from the top to the bottom. So really, in this case, the question that we're trying to ask is, can I show that a dilation occurred? What do I know about dilations? Caden? Good. It's a change in the size of the shape by how much? What do we call it? A scale factor. Okay. So what we're saying about dilations here is, can I show that the ratios of side lengths or, this is going to be the easier way to do it, the ratios of side lengths or coordinates is the same. If I wanted to show that the side lengths are the same, I would have to find the distance from A to B and B to C and A to C and compare those to the side lengths of D to E, D to F, E to F, and then I would have to compare them to each other. Okay, so what we're going to do instead is that a dilation occurs when we take an ordered pair, xy, and we transform it to kx and ky. If I can find k, I know that a dilation has occurred. Let's start with A to D. So since I can do the image over the pre-image, I can take, well, the coordinates of D and say, well, 1.5 started at 1. And I want to know, is that the same as what we did to y? Well, what did we do to y? We started at 1 and went to 1.5. So is that the same as 1.5 over 1? And is that the same as 3 to 2? And is that the same as 4 to 6? And is that the same as 3 to 4.5? I'm sorry. Uh-oh. What did I do? I switched them. That's what I did. 4 to 6 and 6 to 4. Gone and went upside down again. I think this is the only class I make this many mistakes in. Probably not. Just pay attention to it more. So 4.5 to 3 and 13.5 to 9. Let this dry here for a second. What do all of these ratios simplify down to? Are they all the same, Cade Nielsen? Yeah, this would just be 1.5. So K would be 1.5. So they are similar. And let's see, this one was my 6 to 4. Okay, so they are all 1.5. So that's my scale factor. So I know they're similar because there's a dilation that takes me to them. Cool. Let's look at just a couple examples. I think we can be good in our notes here, but let's do these real quick. All right. Are these two figures similar? What would I have to do? And let's be specific about the transformations that would occur. And let's take a look at the names here as well. I want G to line up with which angle? K. So if I want to get G over here to K, what do I need to do? Donovan, give me the first step. Rotate how much in which direction? Okay, so we rotate 90 degrees clockwise. After that would get me to here. Maybe we can draw it in real quick. If I draw this in here, this is what the shape would look like. How would I then get G out to K? By how much? So I want to extend it 4 out, right? But it's 2 away from here. So how far? What is the scale factor to get it there? Remember, I want to multiply. Go ahead, Keith Nielsen. Dilate by, be a little careful here. It's at 2, and I want to get it to 6. So 2 times what is 6? Dilate by a factor of 3. Okay, so are the figures similar? Well, if I did that, this would be out to here at 3, 3, 6, and -6. So yeah, they look like they're similar because I can get a mapping there. Let's do one more here because I think this is important to recognize. We want to find the center of dilation. How do we find the center of a dilation? I tried to draw a bad one in your notes the other day. It just didn't line up real well. What do I need to use? Taylor? Good, yeah, so we just draw some lines through corresponding vertices. So if I draw, and I really only need 2 because they only intersect once. Let's see if I can make this a half decent line this time. Nope, messing up already. Okay, so I've got that one there. That one's pretty good. And then it looks like actually these all line on the same line, so maybe I'll use that one. So where is the center of this dilation? Somebody I haven't heard from yet. Go ahead, Gavin Hart. Negative 2 was negative 2, 2. So the center is there. That's where I started. And I'm starting at A, B, C, D, E. So I'm starting with this outside shape. How would I get it to the inside? What is my scale factor here? Caden, what do you think? 1/2. And let's look. If I looked at the distance here between these two, let's use the one I've got the line on. In order to get from my center to this point C, I would go down 1 over 1, down 1 over 1. I would do it twice. If I want to get to this point R, I would go down 1 over 1 once. That sounds like it went, I went half as far. So my K here would be 1/2. And it proves that they are similar because there is dilation. Still good here?